The simulation that we'll be working with in this example 5.4 has previously been set up, and the instructions for doing that is in Appendix 3.1. So if you haven't done that already, you need to follow the instructions from Appendix 3.1 to set up this simulation. We're now going to go through and make some modifications to it. So firstly, here in the process flow diagram, we'll double click on the reactor on the feed stream, and looking at the composition, we're going to change the molar flows, make them much smaller. 1 kilogram mole per hour of methane, 2 for oxygen, and 7.52 for nitrogen. So we click normalize and OK. So these flows correspond to the stoichiometric requirements for combustion of methane, where we need 2 moles of oxygen for 1 mole of methane, and it's assuming that we're combusting it in air. So this is the ratio of 79 to 21 of moles of nitrogen, 2 moles of oxygen. So we can close that one. If we double click on here and have a look at our reaction, under the details we can see in terms of conversion, we've got 100% conversion. That makes sense. When you burn methane in air, if there's a stoichiometric quantity of air, then we expect to have complete combustion of the methane. And these two coefficients are set to 0. Now on this one, we want to check that the duty is set to 0. So this is effectively 0. So what we're trying to do here is establish the adiabatic flame temperature for the combustion of methane in air. And so by setting this number to 0, we effectively insulate this vessel so that there's no transfer of heat out of the vessel, and so all of the heat that is evolved in the reaction will go into heating up the gases that come out in this gas product stream. So that duty is 0, which is as it should be. So if we close this now and have a look at our gas product, we can see that the temperature is 2026 degrees Celsius. So according to this simulation, the adiabatic flame temperature for methane burning stoichiometrically in air is 2026 degrees Celsius. Our hand calculation gave us 2066 degrees Celsius, 40 degrees Celsius difference. The reason for that difference is due to the simplifications that we make when we do our hand calculations. And the largest contribution comes from the fact that we assume mean specific heat capacities over a range of temperatures, whereas HYSYS will calculate the specific heat of each component at each temperature using the correlations that are built into it.